The concept for EPARTRADE is basically, in my opinion, there's a big hole in the internet. So the internet started many years ago, but there's never been an online business community for racers on the World Wide Web. The need for EPARTRADE is actually quite obvious. Basically, people in the business of auto racing need a place online to hang out and to get their problems solved.
It's extremely simple for a buyer or for a supplier to interact on the platform. The first thing you need to do is sign in, which is free. And the second thing is, when you see a product that you're interested in, all you need to do is click on request more information. If it's a company, you click on request more information, and then from there, it is forwarded directly to the buyer or to the supplier.
You can go to EPARTRADE.com, you become part of a community of businesses in racing, and it makes sourcing products much easier than just on the internet or using Google.
At EPARTRADE, there is no e-commerce. It's literally a connection just like at a trade show. So now, any time of the year, a buyer could reach out to a supplier through an email.
More than that, it's a place to go just to keep current every day. So it's a good place to start your workday in your racing business or in your offices of your professional race team. And you know you're current when it comes to new technology, industry news, technical papers, technical videos, all of that and more. We're not looking for a million hits per day. All we want is people who are really the volume buyers of racing products in the racing industry to be part of the little world of EPARTRADE. We have racing businesses participating from around the world. So you get suppliers from around the world, you get buyers from around the world.
EPARTRADE really eliminates having to travel, closing down your shop. Now you have a place to showcase globally your racing product and technology.
Good morning and welcome to Race Industry Now, the technical and business webinar series from EPARTRADE. I am Francisque Savignan, the founder and CEO, and with me this morning is Judy King. Good morning, Judy.
Good morning, Francisque and Brad and everyone.
Good morning, Brad. How are you?
I'm fantastic. I hope you're doing well also.
Absolutely. So this is episode 108, and we are going to bring back the gentleman from Fluidampr and somebody else, Judy, right?
Yes, we have Greg with Inland Empire Driveline Service. But you know, Francis, it's been a great week already because we've had new suppliers jump on board. I'm sure everybody's heard about Cosworth. They confirmed. I've had some other companies, Andrews Cams and Bill Patterson Artwork, that does commissioned artwork. So there's so many new products and services on board.
Absolutely. And I mean, Cosworth, I've worked with them for many years, and I was delighted to bring them back on the platform. Big, huge name in the industry, a worldwide company, everything coming out of the UK. And so, yes, we'll do a webinar with them pretty soon too. So as we're talking, I see a signal from our producer, Reed Keneski. I see Greg from Inland coming on board. I think we should be seeing Brian and Aaron pretty soon. So good morning. I think Greg is here. Aaron, Brian, very good. Excellent. Good morning, Greg.
Good morning. How are you?
Very good. Hello, Brian.
Good morning. Good morning, Francisque. How are you doing today?
Very good, Aaron. Welcome back.
Good morning.
So, Mr. Brad Gillie will let you take over for the next hour. So we're going to be back in about an hour. So have a great webinar, and we'll talk to you guys soon.
Thank you very much, Francis. Really appreciate that. Really looking forward to this next hour as well. Today's title, Vibration Control, Engine and Driveshaft by Inland Empire Driveline and Fluidampr. And joining us here, Greg Frick, the president of Inland Empire Driveline Service, Brian LeBarron, marketing manager, Fluidampr, and Aaron Neyman, the vibration solutions manager, Vibratech TVD. And if you're new to the format, what we do is we're basically going to spend the next hour talking about our topic of the day and a lot of different things that would certainly interest you as racers. And as always, if you have any questions along the way, please feel free to type those into the chat and we'll get those questions asked in the order that they come. And certainly if we're on topic as well. And if you have a question specific to one of our panelists, please address them as such to make sure we get that. And gentlemen, I just want to say hello to each one of you individually. First of all, Greg, we'll start with you. If you would kind of give us an overview of some of the things that we're going to be talking about here today.
The drive shaft and the crankshaft obey the same physics, and that's why we are together on this presentation. I'll be talking about those things that irritate drive shafts, and we'll follow Fluidampr, who is going to tell us what's going on with the crankshaft.
And Brian, I know you're familiar to our Race Industry Now episodes and everything that we do. So kind of give us an overview of Fluidampr and some of the things that you have on deck for us.
Well, good morning, Brad. Again, my name is Brian LeBarron, Marketing Manager here at Fluidampr. It's great to be back on the program. Yeah, today we're going to be talking about vibration control. But really, why is it? Why do we talk about this? It's for durability. We want to get to the finish line. And if we're not talking about race cars, think about the comfort and durability building into your tow rigs, where you have a comfortable ride going down the road to the track. So Fluidampr, well known in the industry for performance harmonic dampers. So we're going to be talking about how those work, but also why you need it, the dynamics of vibration happening at the crankshaft. On board with me today is Aaron Neyman. He's the Vibration Solutions Manager for Vibratech TVD. Vibratech TVD is the parent company to Fluidampr, and they get into all sorts of vibration and analysis on the crankshaft, the driveline, camshafts, and a whole host of industries outside of racing. So it brings a big, broad perspective.
Well, Aaron, welcome to you as well. And with some of the things that you work on and the solutions that you come up with as well, what are some things that people typically run into? What are some of the things that you have to solve, if you will?
So some of the things that we run into from a solutions package standpoint, you come up with a vibration control for the damper itself, and then that covers the engine, and then you come up with a vibration solution for a drive package, and then you come up with a vibration, a solution for the rear axle. But when you bring everything together, sometimes you get people that, if you're not an OEM car builder, you bring in all these different packages together that are good as separate components, but when you bring them together as a system, you get some vibration issues, and that's why we're working on this today with Greg from Inland Empire to talk about how the different systems come together and interact, and how sometimes parts that are good vibration wise, when they come together, you can have interactions that cause noise issues or possibly durability issues, and what are some ways you can approach fixing these solutions from a driveline standpoint, and also some ways you can fix these solutions from a vibration damper standpoint.
Well, thank you. Well, Greg, let's let you talk here for a minute. The last thing that anybody wants is to either not complete a quarter-mile run, get stuck out in the desert somewhere, stopped on the racetrack because they simply can't move forward because they've had some drive shaft or driveline issues. So give us an idea of what you do at Inland Empire Driveline Service, if you would.
Well, I'm pretty much the outside guy running around doing things like this. But we build drive shafts for everything from steel mills to rock crawlers, and all of them are subject to the same issues and forces. So it's our job, or the job of any drive shaft designer, to put the vibration issues someplace where the vehicle owner doesn't go. So for instance, if you got a Camaro that'll go 180 miles an hour, we can get it calmed down to about 120, and after that it's carbon fiber shaft time. So there's all kinds of different solutions depending on what the car is doing to the owner at the time.
Wow, that's interesting. When it comes to drive shafts, and you're talking about rock crawlers and different things like that, as people are changing geometry of suspensions and all of that, obviously that changes the length and all of that. How long can a single piece drive shaft be made?
That has been an ongoing issue for a very, very long time. Currently, OEMs are out to about 72 inches in pickup trucks and Suburbans and the like, but they're using 5-inch diameter tube to do it. In those cases, if you fiddle around with the wheel diameter or put a chip in your Tahoe or put a couple of turbos on it, you can all of a sudden find yourself into a physics problem that will drive you mad.
And, when it comes to driving you mad, I know you guys offer a variety of products, not just the Driveshaft itself, and have an amazingly incredible 48-hour turnaround service as well. But if someone just thinks, hey, I have this vibration here, I need this fix, that's not always the answer, is it? Just what they think they might need because of so many different variables involved?
That's true. And one of the things that I like to include in any such seminar as we're having here is do not throw money at wheels and tires when you encounter a vibration. You got to sit back, think about what the vehicle is supposed to be doing, have a bunch of knowledge, and you can figure it out. After all, the drive shaft's made out of metal, so is the car. We ought to be smarter than that.
That's true. Well, Brian, if you would kind of give us an idea, and if we're talking to racers here, and if we're talking to people who, and again, anything from their vehicle, whatever it might be it a race vehicle, we talk about rock crawlers and different things like that, to tow vehicles and everything else. What are some situations? What are some, things that come up that people should be aware of?
Well, again, Greg brought up a good point. You got to sit back and think what's going on. And we start at the engine itself, and at that point of combustion, you got a lot of force building up. And just to show just how much force, I can share my screen here for a minute. Oh. And bear with me as I fumble through the computer here. So when you look at the pressure building up inside the cylinder, and there's a big difference between diesel, which we're looking at here, and your big box Chevy, the red line below. We've seen cylinder trace, pressure in that cylinder build up over 17,000 PSI. That's a heck of a lot of force being applied to the crank. So that much force, the crank's going to want to twist a bit ahead of its natural rotation. Now the crank is just a big solid, it's a mass. And it has weight and it has inertia. So when you twist it forward, it's going to want to spring back. And that's springing back and forth as you go into the firing order, that's going to set up vibration. Now, uncontrolled, that vibration is going to hit your main bearings. It's going to throw off your timing. So that's where the damper comes into play. It's, we don't talk about dampers like we do, turbos or fancy wheels, and it's not a really hyped up product, but it is critical to the durability and the longevity of the engine. So putting a good quality harmonic balancer on the engine, it's going to help settle down that twisting and rebounding of the crankshaft. That's going to just help the engine run more efficiently, stop that vibration from going into the into the transmission and the driveline side as well too.
That's fascinating. It's interesting when you talk about something like that. Like, in my mind, I'm thinking going, okay, from the engine all the way back. But what you're saying is, it also goes back the other way, back toward the engine. If you run into these vibrations, how it can impact everything along the way.
Correct. You're correct. If you don't control it, it's just going to want to keep twisting and rebounding, and vibration is going to travel back and forth. And again, if I share my screen again real quick here, we can model it and see what it looks like. And you can see that whipping motion of the crank. There we go. So here we have a model of the crankshaft, and you can imagine the combustion going on, that force hitting it, and it's going to want to twist it up, rebound, twist and rebound. You can see where it lights up, where the stress points are on the crank. So again, we want to smooth that out. And like I said, by doing so, you're just going to add durability and smoothness to the engine.
Wow, that's pretty fascinating, actually. Aaron, when it comes to finding solutions, if someone is feeling the vibration, how do you isolate something like this? How do you say, hey, here's where the issue is, but then also here's where we fix it?
So one of the things that you have to do in order to find the issue is well, first you have to figure out what kind of vibration is present. I'm going to share my screen now real quick to show a quick diagram of the different types of vibrations that you can see in the engine, because it's not always torsional, rotational vibration. There's also different kinds of vibration that you see. So if we look at this slide here, so if we look at this slide here, it shows a quick diagram of the different types of vibration. Everyone's very familiar with an unbalanced vibration. That happens, one time every time the rotating assembly rotates, and that tends to amplify with speed. And everyone's very familiar with how to treat an unbalanced condition and get your balance back in order. That tends to be a lower frequency vibration because it only happens once every time it rotates. Your torsional vibration, when things start to twist end to end, like the crankshaft model that Brian showed, that happens usually related to the firing order. So on a 4-stroke engine, it's half the number of cylinders that are firing. And what that simulation image showed a picture of the vibration with the crankshaft fixed at the flywheel end. But in reality, when you're out with when you're out racing, that end isn't necessarily fixed. It's a little more stable. So the end-to-end twist still happens. And when you get that end-to-end twist, a lot of times road-going vehicles, OEM vehicles, have another vibration absorber at the end of the crankshaft. I would imagine most racers are familiar with like a spring pack in the end of in your clutch disc, and that's a torsional vibration control device. Dual mass flywheels, which are more of an OEM solution and less of a race solution, and then even torque converters, different things like that, kind of decouple the drive line so you're not passing as much vibration into your transmission and into your drive shaft. But I mean, as you're familiar with a lot of racing applications, you deviate from, let's say you're pushing more power, so you want to push a different style of clutch disc, or you're looking at, sometimes they'll go with a solid disc without the torsional spring pack in there, or you'll go with a multi-disc setup and you're changing the weight at the end of it. You're also changing what vibration you're passing on from the engine further into your transmission, which can cause gear rattle at discrete speeds, or even just accelerated gear wear. And you're passing that into your drive shaft too, which can also amplify some harmonics from the drive shaft movement too. And that's something that if you're passing stuff on from the engine, you want to get a good quality damper on the crank nose to help keep the engine happy, to keep your bearings happy. And then you also want to look at what you're doing at the other end of the crankshaft. So if you're running a solid disc clutch, you're going to want to look at, you're going to want to be spot on with your drive shaft configuration. And you're also going to want to make sure that everything else is in order. And you kind of have to plan for this stuff if you want to have a good solid package vibration wise and durability wise.
Aaron, is it possible that, all of a sudden this is the vibration I'm having now and we fix one thing, but now maybe it creates another type of vibration problem?
Yes, that happens quite often, actually. So one of the things that Greg actually mentioned is that you want to put the vibration in a place that the car can't necessarily reach it. And a lot of times that's either below idle or below low RPM speeds from a torsional vibration standpoint. If anyone's familiar with inline six vehicles, some of the older stuff before dual mass flywheels, I had an old Dodge pickup, and one of the things that I've noticed when I was learning to drive on that, it's the old slant six, the leaning tower of power Mopar. If you loved it, you could actually make the whole truck bunny hop down the road because there wasn't a decoupling really well there. And where most modern stuff have dual mass flywheels like BMWs and stuff like that. So, if you would put that below idle, and then you start lightening everything up, like let's say you go with a lightweight flywheel, when you take mass out of the system, those vibrations will creep up and higher into the RPM range. So that's something where you might have a good solution when you start your build, but then when you start changing different things down the drive line and changing your masses, you might want to be prepared to have extra testing time to figure out what you need to get out the whole system to work together happily.
Again, and thank you for that. If you have a question for any of the panelists, please feel free to type it into the chat. We'd love to be able to talk about what you want to know about as well. Greg, if I call Inland Empire Driveline Service and say, hey, this is what I have, this is where I'm going, I need a custom drive shaft, what do I need to know? What kind of information do you need to help me get what I need?
We've got that boiled down to 3 dimensions. We need to know how far apart the 2 immovable objects are. That would be the pinion yoke and the output shaft of the transmission. We need to know how much spline is hanging out past the seal on the transmission. And we need to know the breadth of between the tabs that center the universal joint in the pinion yoke. We got this all boiled down to a form, and you check a box. X is this, Y is that. It's a whatever it is transmission. And then we're ready to go after we start getting questions answered about how much motor is this thing got? Did you forget to tell us about the nitrous button? That kind of stuff.
Yeah, which does beg the question, application. I might have, an engine with 650 horsepower, but if I'm going drag racing versus going, desert racing or something different like that, does that change what my application is going to be? Not just the power that I'm putting down, but the application in which I'm using it.
And not particularly. Again, these things all obey the same physics. So, in the desert, you got rocks. They're going to bang into things. On the drag strip, hopefully you don't. But it's more an issue of that X dimension between the 2 immovable objects. As that thing grows, the diameter of the tube has to grow with it to bridge the distance. And when you're ready, I'll get into the Mother Nature part of this, and that's where the length issue comes in. Diameter is strength, and the wall thickness of the tubing is pretty much irrelevant. It's the diameter that provides the strength. And while I'm on the subject, we're not too scared of horsepower. It's torque that bothers us. And as long as you can break tires loose and make a whole lot of smoke and polish the track, we don't have a problem. But if you hook that baby up, now we need to talk.
With the company, with Inland Empire Driveline Service, it's not just drive shafts, yokes, U-joints, center support bearings, and all of that. When I'm looking at something new with one, how far do I need to go with everything that I'm changing along the way in that as well?
If you decide to put an overdrive transmission in where a direct drive was, we need to talk. If you stick a chip in the computer, you probably ought to be thinking about, gee, I just upped the horsepower by 200 and I still got this old junkyard drive shaft in here. Maybe I ought to think about that. So literally anytime any individual component gets modified, you have to remember that all these components are talking to each other. And this business about putting the conversation someplace where you don't go is really important, because again, you get into the Mother Nature's physics, and under the wrong tube diameter and length situation, drive shaft will explode. It looks like Elmer Fudd shotgun in the middle. And there's nothing else that makes a drive shaft look like that, except you've got too much RPM and not enough diameter.
I like the analogy right there.
That's exactly what it looks like.
Yeah. Wow. Brian, a question for you from one of the panelists. Can you list the benefits of using a fluid damper harmonic balancer over OEM on a performance engine?
Sure. So the OEMs, we talk about this being a system of weights and masses and under stock conditions. That OEM harmonic balancer is tuned for the stock conditions. Two things are going to prematurely make it obsolete. One is if you start building up torque, you're going to overwork the stock elastomer damper. The rubber is going to crack and bulge and wear out. The second is if you start changing those masses in the rotating assembly, lightweight pistons, different connecting rods, changing the mass of the flywheel or the flex plate. Now you're changing the resonant frequency of that whole system. The stock damper is no longer in tune. So Fluidampr solves that two ways. One, it's a viscous type damper, it's highly durable. Two, it works across a broad RPM range, so there's no tuning involved with it. Beyond that, the Fluidampr is SFI 18.1 spec for professional racing. And we try to make it as easy as possible. It's all based on basically your make, model, and engine, and just a simple lookup and hit the purchase button.
Is there a situation, let's just for a number, I've got 650 horsepower, but now I'm thinking about maybe down the road adding nitrous or doing this, and I'm going to up it by 200-300 horsepower or whatever.
Yeah, the beauty with the beauty with the Fluidampr is that the inner inertial ring is not bonded. The harder you make this work, the more it shears through that silicone, the more effective it becomes. So again, horsepower is not big of a concern. We're very well known on the performance diesel side, where we're seeing upwards now of 3,000 horse and equally about 3,000 foot-pounds of torque. So they say very highly durable. Viscous dampers did originate and really became popular in the commercial industrial engines, and it was just basically downscaled for racing applications, and then refined for high RPM use.
Aaron, as Greg's describing what happens to the drive shaft and all of that too. Well, now you've got that strong enough, and now you've added horsepower. Now you've done this. What kind of risk do you run in blowing something else out along down the line?
So one of the biggest things that that Greg mentioned is if you're changing the RPM of your system. So let's say you're doing some work on your valve train. And you're strengthening up your valve springs so that way you can turn more RPM, changing your camshafts so that you're getting the the right cam profile to push more RPM. If you keep pushing your RPM ceiling higher and higher, you run into a point where you might actually hit a different vibration resonance frequency. So let's say the crankshaft has a certain resonance, and a lot of times OE design tries to put it in between cranking speed and idle speed. And then you hit a second resonance later on in the higher RPM range. It's an RPM that nobody really sees in a stock application. But as Brian mentioned, especially with performance diesel, where they're pushing these engines more and more RPM, they'll start like a high RPM, they'll do a high RPM dump for pulling, or if they're doing like dyno, there's a multifaceted competition that a lot of the diesel guys do. Where they'll do like a dyno aspect, pulling, and then a drag race. And if you're looking at all those different things, if they're pushing more and more RPM, they're more advantageous for those different parts of the competition. And we've seen cases where a second resonance will come in, and a lot of times that second resonance is outside of the range of the rubber tuned OEM dampers. And those particular ones they're really more of a tuned absorber. If you look at it from a textbook, where they only work at a discrete frequency. So they'll start resonating kind of like, if you play a certain pitch, if you have like the decibels, or like the water glass, where you see the water glass start to go into resonance at a certain pitch. Well, that's how the rubber dampers work. But because the Fluidampr isn't bonded, so that ring is free to move around at any frequency, you get more of a bell curve of effectiveness. So that way it can cover multiple resonances without having to change your damper. You touched on it a little bit earlier with like a nitrous situation too. So if you're increasing your power level without changing your hard components, your vibration peak isn't going to move around with the viscous damper because the masses are all set. You're not necessarily changing anything, between the two, and you're not changing your resonant frequency. Where with a rubber part, we see this a lot from Vibratech when we do marine retrofit applications. And we've done marine retrofit applications for almost every generation of GM small block on an OEM level. And if you're familiar with marine, you're either idle or full throttle. When you set on full throttle all the time, the damper will tend to heat up. And the rubber ones, they can actually soften the rubber and shift the peak further down into the RPM range. And then that's when things start to come apart. Or with the viscous damper, if it starts to heat up, your peak might get a little bit higher or lower with temperature, but it doesn't shift around to different RPM ranges. So you still know what to avoid with either different shift points, or you can tell the driver, you run at this RPM for this amount of time during the, like if they're on a long straight track, you can really wind it out and get through it and just have them push right through that RPM or different things.
We have another question from chat. I don't know if this is for Aaron or for Greg or maybe Brian, but it says, how can you deal with an engine TVD if it doesn't have a crankshaft nose to fit one onto?
Okay, we've done a lot of work with OEMs that have dampers built into it that are more of an internal component. So a lot of times, if the damper is an internal component, there's still some sort of a mounting flange inside of the engine, and we've done a lot of work on those. With those are typically actually are pretty high RPM applications. Like we're looking at 10,000 plus RPM, and usually there's mounting provisions either inside of it or you have to come up with a special cover in order to expand it. But then once it's run in an internal part, you can downsize the damper a little bit and use the engine's oiling system to cool it as well.
Oh, interesting. Brian, I think this is probably for you regarding the fluid damper. Does that silicone fluid break down or have its viscosity or shear characteristics change over time?
Well, one of the beauties about using silicone is that its shear properties remain pretty consistent from about minus 40 degrees to 300 degrees. So in there, it gives you a nice consistent shear effect. Now, as far as breaking down, in the heavy duty viscous dampers we see in like Class 8 trucks, big gen set, those that are under heavy torque, constant use, typically about 15,000 hours or 500,000 miles, the silicone will start going like a polymerization process where we'll start breaking down. So we do say in the heavy duty side, and this may apply to those out there with tractor trailer tow rigs, or if you're using your light duty truck as a tow rig, you're getting up there 500,000 to 1 million miles on it. A good idea to replace the viscous damper in that situation. In street and track and racing, it's good for the life of the engine.
Okay. Greg, if we could take it back to you here for a second, and let's start talking about angles and the maximum angle a cross and bearing joint can take.
The smooth power that fluid dampener has created for us coming out of the back end of the transmission is, as they have stated, not smooth. There are firing impulses coming from the engine and they kick that crankshaft as they have described. So, but for simplicity's sake, if we assume that we got nice smooth round power coming out of the back of that engine, it hits an angle. Get this up high enough so you can see it. When it hits a U-joint angle, the joint has to speed up and slow down twice per revolution. So now this thing is pulsating power, and the whole drive shaft is pulsating, and you have an equal opposite angle on the back end at the transmission or at the rear end to take that pulsating power and turn it into smooth for the rear end. Typically 3 degrees break through the U-joint is about all you want to have to live with, because you can feel it if it's more than that. And as the RPM increase, the angle that those parts will successfully turn through goes down, along with the life of the U-joint. But the thing to take away from that joint angle deal is that the drive shaft is always pulsating. This is true of any cardan style cross and bearing sort of U-joint.
Okay, Aaron, I saw you kind of shaking your head just a little bit as Greg was describing that. Did you want to add to that at all?
We actually have a machine in our engineering development area that we use for accelerated durability, and it has a cross style single U-joint. It's got a central shaft for the flywheel, and it's got U-joints, and then it has flanges on both ends on a secondary shaft. And we can crank up the angle on that machine. We can do, we typically run at about a 20-degree angle, and you can actually watch the face of the damper slow down and speed up 2 times per revolution at low speeds. And we use that. It only runs about as fast, about 1200 RPM, because beyond that, it'll start shaking and walking around the shop. But you can see a lot of speed variation in just that little bit of RPM, when you change the U-joint angle like that.
Wow.
One thing that he touched on is if you have angle at one end and no angle at the other, then you're not getting rid of that pulsating power. We know for sure that you cannot exceed 6 degrees at the transmission end and have 0 at the pinion end and expect it to work, because one of our customers did it and made it 300 miles down the road before the pinion welded itself to the ring gear. So the forces we're talking about here are enormous. And that's the worst case, but typically people can feel when these inertial vibrations are not happy, and if you don't do something about it, you're going to destroy something way more expensive than the drive shaft.
So are you saying if you have angle on one end, then you have to have angle on the other end as well? That's the equal, or how does that work?
Yeah, that's exactly how it works. If you have an engine sitting in a frame at 3 degrees down, which is a world standard, and you have a drive shaft, get this up here. If this is 3 down, the shaft is level, you want 3 up on the pinion so that this angle here completely cancels this angle, and the pinion works both sides of perfect. Now, the drag racers are going to say that's not true. You want to have the pinion down because it's going to wrap up, and it does. But most people drive their cars at some position other than pedal to the metal. So we're talking here about driving it on the street and being comfortable. But yes, these angles need to be almost exactly canceling each other, because this green thing is speeding up and slowing down twice per revolution, and you got to get that pulsation out before it goes into the rear end. This is why axles break.
Wow. Well, while we're talking about that, then how much uncanceled angle can a drive shaft take?
The drive shaft, Spicer says that you can live with a degree of uncanceled angle. And that's pretty much, working both sides of perfect at the back end. And, you can do anything you want as long as it stays in the vehicle and you can put up with the vibration. But again, if you're going to hop in your car and you're sitting in Ohio and want to drive to LA, you don't want to be thinking about how you've got a drive shaft in the car. You want to forget it.
And is it fair to say, like with suspension travel and things like that, as the suspension moves, so does the angle on both ends?
The angle at the rear end moves more because you've got, we all remember our high school trigonometry, right? So if you have this going on at the rear end, you see it doesn't move much up at the front. The only time this becomes a huge issue is there's always an offset in the plan view because the pinion runs off center. And so if you're building a Cobra or a Bucket T or something, a drive shaft's a foot long, now all of a sudden you can get huge angles in the plan view, and you got to do something about that, or buy one of those trailer things.
All right, back to the chat. And again, if you have a question, just type it into the chat, and we'll absolutely do our best to get to every one of them that we can. Brian, I don't know if this one may be more for you or not. What do you think of pendulum absorber dampers as fitted into flywheels?
Well, that's an excellent question. I always want to punt that over to Aaron, thinking as a total package, because now we're going to add the pendulums are there to help cancel out the vibration. They're putting it on the back end of the flywheel. I mean, you're still going to get some twist up in the front at the snout. But Aaron, you want to chime in on how effective you think that may be?
Sure. So the big reason for the pendulum damper is they work very well when the order counts. So when I say order, I mean number of vibration pulses per revolution. So like the drive shaft is the second order, firing on a V8 is the fourth order. So if you have your pendulum count multiples of the vibration for the firing, they're going to do a good amount of work to reduce that vibration, because when the firing pulse comes through, if the number of pulses is equal to or a multiple of the number of pendulums in the pendulum damper, it'll cause those to rock back and forth in the pendulum action. And they're used a lot on like aircraft engines. I believe Lycoming is one that uses them quite a bit, and they're actually built right into the crankshaft throws, and they work really well for discrete RPMs. And the pendulum damper is used a lot on the back end of the crankshaft, either built into a flywheel or built into a torque converter to cancel out what's left from the crankshaft twist before sending it downstream to the transmission and the drive shaft.
All right. Another question, are there any vibration issues that any of you encounter that are more specific to compound boost vehicles? Any general cautions for compound boost applications?
So the compound boost, mainly what that does is that'll change the look of that cylinder pressure peak that Brian shared earlier in the presentation. Instead of having a nice smooth solid peak at a certain angular event in the firing, because it fires 2 rotations, so 720 degrees. So a lot of modern engines have timing wheels, so that way your engine management knows exactly where your crankshaft is in the rotation, so it can time the fueling with the cylinder pressure, when the compression comes on, and so you can get your ignition at the right spot. Well, with your compound boost, when you're running those, you're changing a little bit the profile of that firing peak, and that can also have a little bit of an effect of not necessarily how the crankshaft rings out, but the way that you strike the crankshaft. So that has a lot to do with the input power into the vibration damper that causes it to heat up. And the viscous damper is pretty forgiving with that. They'll reach a stabilization temperature really pretty quickly when it's in operation. They don't tend to really suffer much from heat soak because they're designed like a radiator. So you have a certain amount of power input that it can handle just by the design of the damper. Where like the rubber parts, if you heat them up too much, that rubber properties will change, and then the vibration starts moving around, and you can actually get a worse vibration settling into an RPM that had no vibration before.
How about four-wheel drive applications? How does that change the game and things that I need to know?
Don't go more than 4 inches on the lift, or buy U-joints by the case. That's about all there is to it. Because you create these huge angles that we talked about earlier, and huge is like more than 5, and then drive it down the highway, you just take the life out of the joint and nothing flat. I'm sure the people that build lift kits are real thrilled to hear me say that, but again, any confrontation between artistic stance and Mother Nature's physics is going to get won by the physics.
Every time, I would imagine. Or
Every
here,
time.
here where I am in North Carolina, where people want to take their four-wheel drives and squat them, I would imagine that that really changes the game.
Well, some of what they're doing there is, anything you do to make the rear shaft happy so you can drive down the road makes the front shaft worse.
Also makes it pretty hard to see.
Yeah.
Yeah, they actually changed the law here recently to give a maximum angle that you can or cannot have, if you will. I just think the aesthetics are justification for law enough. But anyway, that's
You can get the
No
same
accounting
thing
for
for all
taste.
enough gravel.
all right. Let's see. I want to make sure I get to these. All right, here. Many people might benefit from some discussion of U-joint phasing, especially with multiple section drive shafts. I don't know who the best one is to take that. Greg, Aaron.
Well, I suppose it's my sentence. Typically on a 1 or 2 joint shaft, the ears on each end of the shaft are squared up with each other, and that's phasing. To the best of my knowledge, there have been 2 vehicles that came misphased from the factory. One of them was a Camaro 4-speed with a 4-barrel back when. The other one was a 58 to 63 Chevys. They had all kinds of trouble with vibration and tried to correct it by 90 out in the middle. But essentially, if you look at it from the standpoint of what's a common rule of thumb, just line all of those yokes up so that they're square. If you're, say, in the drag racing business, or you want to keep an eye on your aluminum or carbon shafts to make sure they're not starting to yield, you just put a couple coat hangers or welding rods on those ears and look down them. As long as they're square with each other, life is good. When they start to drift, get it out of there.
Interesting. Aaron, did you want to follow up on that, or Brian?
That was just another thing too, is touching on what Greg mentioned. If you got a nice bright aluminum drive shaft, if you take a straight edge and actually just draw like a paint line down it, if that line starts to move, then you're getting some yielding too.
Okay.
Doesn't happen much, but there's no such thing as too much attention.
Right. And it's a quick way to inspect it at the track too, without having to use too many tools.
That makes sense. How do you decide what material to use for a drive shaft? Aluminum, steel, carbon fiber? What goes into that decision?
Again, it's become much clearer over the last decade. Aluminum drive shafts exist primarily because of overdrive automatic transmissions. They increase the torque demand because you got a 0.7 overdrive and horsepower requirement stays the same, but torque goes up. So the frequencies being fed into the drive shaft that cause it to react will migrate back into the transmission in the rear end. This is the conversation that these parts are having all the time. And the less mass you have speeding up and slowing down twice per rev under that car, the happier the overdrive clutch pack is. So it's an investment in longevity for the transmissions. And I hear from the guys at Tremec that they like to have the joint angles below 3, because as was mentioned earlier, at some speeds you can get the gears rattling in a transmission, and they don't like having some customer tell them their transmission sounds like a box of rocks. So the less angle there is and the less mass there is behind any overdrive is a reason to go to aluminum. You go to carbon for totally different reasons. They are excellent at getting rid of harmonic issues. They live in hostile environments. They've got a place, as I mentioned, in that one of the Camaros. I think it's a Gen 3 or 4. I can never keep them straight. They got a built-in resonance from the factory. we can chase that to 120 miles an hour. And after that, if you want to go faster, it's carbon shaft time.
Okay. It's interesting in talking about all of these things. And, when we start to talk about very specific applications, do you ever get rid of all the vibration, or do you say, here's where I'm going to live in this car? If it's a dragster, you're going full on, or if I'm doing this at this RPM mostly, is it where I need to solve my problem in this range where the vehicle is mostly going to travel?
That's it, the last one. These forces and all this activity is going on 100% of the time under your seat. And you want to put these dangerous places like critical speed and half critical into some area where you just don't go.
Okay. Brian, you mentioned earlier, you talked about, diesel and different things, and torsional vibration. Does it differ between different engine configurations, V8, inline six, gas, diesel? How does that change?
Well, it does. And earlier when I brought up the slide, it shows just the difference between a performance diesel application and just a big black Chevy. We're at 17,000 PSI on the diesel and about 1,100 PSI on the big black Chevy. So the combustion forces within diesel are just greater. That's why diesel engines are a bit more robustly to handle it. But in different configurations, it is true. With a V8, the crankshaft can be longer than a V6. So you just have more mass, you have more firing orders. And then if you take that down to the inline fours, now you knock out two more cylinders and you have different dynamics of vibration. So when we talk about dampers, the Fluidampr is a broad range damper, is very forgiving, but it is designed for the application that it's going on. So you can't run an inline four damper on a V8.
How does it work? How does a Fluidampr work? I know you showed us a neat little cutaway and all of that, but what are the mechanics there?
Right. I'll pull that up again here. We can all see it. So we have the outer housing. We have an inner inertia ring. It's maybe difficult to see, but there's a little tiny shear gap between the ring. Here's a business card between the ring and the. Oh. All right. Oh, I see my camera angle just cut out here. Now we go. There we go. Get the angle. And that card just barely fits in here. So you can see that shear gap in there. That is not much space at all. There is more provisions for silicone in here. So the damper has silicone pressure injected through the fill holes, fills up that gap there. And it's the rate of shear that this inner inertia ring is moving through the silicone. So it turns that vibration into heat and then radiates out the outer housing.
Okay, it's fascinating, the technology and the way all of that works. Greg, I want to ask you, we keep talking about things and cars going fast and all of that. What's the fastest one of your drive shafts has gone?
Customers don't give us that feedback very much, but we do know that orange dragster up there did 286 in the quarter. And we have another customer that also ran 286 out at Bonneville. So we know for sure this stuff works well up to 286, but beyond that, nobody has reported yet.
Well, the interesting thing there, though, is 286 at the end of a quarter mile is one thing, but 286 going down Bonneville, what is that? Like a 1 or 2 4-mile run? So the difference in actually doing that, like hitting that peak versus sustaining that peak.
Yeah, that's why we got to talk. What works on the drag strip does not necessarily work on the lakes, does not necessarily work on a circle track, and none of them work on the street real well. So you set the car up for what it's going to do.
Aaron, you want to elaborate on that some too?
So just touching on a little bit about the speed parts of it too, and not necessarily top end speed, but engine RPM. One of the big misconceptions about Fluidampr is people talk about how they don't work beyond a certain RPM threshold. And we're actually, we were on an OEM level. We designed and created and manufactured dampers for engines that out of the box reach an 11,000 RPM peak. Not just a crankshaft damper, but they also have camshaft dampers because their cams go into resonance because they push so much RPM. Then also one that's, I believe, 12,000 RPM as well. That one's actually just coming into production pretty soon there. So, I mean, some of the fastest revving engines in the world, like Lexus LFA, use viscous damper technology. Formula One engines have their dampers on them. They're just internal components, so you really can't see them when you look at it from the outside. So, I mean, realistically, like Greg mentioned, you have to have a conversation about what you're going to design your engine to. What are your RPMs that you're looking to run? Do you have any critical speeds that you notice right now? How much of the rotating assembly are you going to change as you build it? You mentioned nitrous, so you're going to add that later on. What kind of turbo setups? All these are very important to get everything to start, like Greg mentioned, all these components start talking to each other. And the best thing you want to do is, inform the suppliers that you're working with of as clear of a picture as you can give them. So that way we can give you guys the best solution available that'll help your whole car communicate well.
All right, let's say I'm just, full on geek for all of this and I'm ready to do a deep dive in whatever build or whatever thing I'm working on. Is there an order? Greg, if I just go to you first, are you going to help me with what Brian offers with Fluidampr, or, maybe consulting with Aaron? Is there a way that I need to go and approach this?
I now know more about vibration dampening on engines than I did an hour ago, and I knew nothing then. When we built our street rod, I've been at this for 40 years, and I was shocked to find out you can't decide anything until you know what the tires are going to be. Can't pick out your rear end gear ratio. You got no idea about what to do with the drive shaft, obviously. So we want to be last, and typically everything's got to be bolted in the car where it's going to stay. You don't want to be doing this twice because you changed your mind. And then we have these conversations. Okay, what did you build? I think the most useful piece of advice I could offer anybody listening to this would be to sit down with a piece of paper and think about what you're going to build and what you're going to do with it when it's finished, and then build a car that way. And be very, very careful about people trying to influence you about saying that's stupid. Why don't you do this instead? Because now you got to go back and redesign the whole powertrain.
Brian, how about you? Trying to figure out exactly what product I might need for you, or how your solution can help me in what I'm doing.
Right. And again, sitting down, thinking about what you want to do and also what your future plans are. The stock OEM damper in general, it's good for adding an air kit, an exhaust, maybe a tune. You go beyond that and you start with your big power adders, your turbos, superchargers for sure. You're going to want to upgrade the damper then. And then if you touch anything mass-wise within the rotating assembly, you're going to want to switch over to a fluid damper for that broad range damping ability.
Okay, and Aaron, as far as what you have going on with Vibratech TVD, how can you help?
So one of the biggest things, another thing that we touch on too, is planning on having space for a damper. A lot of times if you're building, you've got an engine builder, especially on if you get into the top level racing, you have a separate team that builds the engine and the powertrain. You have a separate team that builds the race car chassis. So if you're getting to that point there, what you want to do maybe early on when if you're getting into your engine build, maybe have a quick call or discussion, with the guys in our sales department, or just figure out what you need on the end of the crankshaft, because the engine actually will perform better with a little bit of weight on the end of the crankshaft. For the damper to do its work, it needs a little bit of weight to work, and that requires a little bit of size. And we can get pretty creative with the size of the damper. We do an inline 6 one that's about 8.5 inch diameter, but it's only about 3/8 of an inch thick. So it's not adding a lot of weight, but we're adding a lot of vibration control potential. So if we have an idea of, like Brian said, what are your plans? What are you looking to do? Powertrain configuration. You want to plan for the weight that's going to be, you want to plan for, having a little bit of weight from the damper. and then plan on having the size that you need. And also, if you need drive configurations, like let's say you have a dry sump oiling system, you want to plan that. Maybe a little bit of an idea of your timing drive too. So if you're going with like a gear driven timing, you might want a little more damper, because if you're running it off the front of the crankshaft, it's going to transmit everything from the front of the crank nose directly into your valve train. So we want to get a kind of an idea of exactly how everything's going to start working together. And also if you have, you're going to go a solid hub, a solid clutch disc on the back end, or if you're going light on your flywheel, you want to make sure we build in enough damper and have space for it.
Okay. Greg, let's squeeze in one more quick question from the chat before we wrap up here. Can you advise a nifty way of deciding how much end float nip you should have on hook joint caps? Too much burns them up and too little allows tube float off center.
Not sure I understand the jargon, but if I do, it means how much end play can there be in the U-joint, and it should be less than 1,000th. Greasable type U-joints we've found brand new in the box with as much as 15 and 20 thousandths end play. And as regards to how tight you can make the bearing portion of it, that leads me to my U-bolt thing. Everybody over tightens U-bolts. And that's why the rear joint burns up first, and it always does it on the pinion side. Proper joint or U-bolt torque has come down evenly until the lock washer just flattens out, and give them 1/8 of a turn and you're all done. That will solve 80% of the vibrations we run into.
It's amazing how much how much over tightening can cause a lot of problems in anything that you're doing. Gentlemen, Greg, Brian, Aaron, thank you so much. This has really been a fascinating hour, and I think we could probably do 2 or 3 more and still continue to learn a lot of things.
Yes, we can.
I've enjoyed it.
There's no end to it.
Thanks for having us.
Thank you for having us on.
Very much.
I think we'll invite you back, right, Gillie? I think yes, we'll find a way to do a part 2 maybe of this. And thank you very much for sharing so much knowledge, so much expertise. And Brad, thank you very much. So we will be back next Wednesday at 9 o'clock Pacific again. We're going to be talking coatings with Oerlikon Balzers. This webinar has been recorded. It will be posted on the EPARTRADE platform in a couple hours, as well as on our YouTube channel. Thank you very much for being with us today. We have pushed Inland Empire and Fluidampr's product back to the homepage of EPARTRADE. So as Judy mentioned to you many times, we're live every week, once on Wednesday for an hour, but the platform, the epartrade.com, is open 24/7, 365 for all of you within the industry to go on, connect, engage, and please take advantage of it. We build this platform for you, for the industry we love so much. Thank you very much, and we'll see you guys again next Wednesday.
Thank you.
Take care, everyone.
Bye.
Bye.
Registering on EPARTRADE is easy. Fill out your name, email, phone number, and create a secure password. Next, select your business type. Choose supplier if you're looking to display products or services and connect with buyers. Choose racing business if you're looking to find new parts and connect with suppliers. Choose race team if you own or are a member of a professional racing team. Begin typing your company name. We most likely already have your company in our database, which you can select from the drop-down. Then, enter your job title. Choose Claim Company if you'll be editing your company profile. Other members of your company can choose Join Company if they'd like to use EPARTRADE as well. You can view and agree to our terms of use here. If you'd like to receive our weekly newsletter, choose Accept. Click Register Now, and your registration will be submitted for approval. You'll need to confirm your email once it goes through. To keep our platform industry only, you'll be approved shortly after. If we require additional proof of business, we'll reach out. Welcome to EPARTRADE.